To understand the working of vanilla recurrent neural network, first of all, we should know the architecture of RNN. That is, it is composed of single memory cell which is getting input from bottom and output from at the top. This is known as hidden unit. It is getting previous input. This unit is getting replicated with the timestamps. Here we will have three weights. One weight is associated with the input channel, that is X2 hidden state. The other weight is associated with the hidden state to hidden state. The one weight is associated with hidden state to output state. To understand it, let's assume one numerical. Let's assume we have been given this is the sequential data and we want to predict the output at each of this input, and WXH is given as 0.5, WHH is given as 0.2, WHY is given as 1. So in this case we want how does it process? First of all, step 1 will be, it will work as the it will work same as neural network. If we have these many inputs, like H1 is having input 1, H2 will be having input 0, H3 will be having input 0, H4 1, H5 0, and H6 1. And we want to predict the output at each unit, and this is how the input is given to the RNN model. Here vector v, which will store the output of previous unit. Initially it should be equal to 0. Then we will have the output of this H1. Here we will have the output of this H1. So in this case, this is at timestamp T0, this is at timestamp T1, T2, T3, T4. Okay, and this is at timestamp T5. So we can see that this architecture is getting replicated with each timestamp. So now we will see how this information will be processed. So here you can see that H1, the output H1 will be calculated as, here we have two inputs. That is, one is getting from the previous timestamp, which is initially 0, that is and one we are getting from the bottom side, that is X, which is equal to X. This X is equal to 1. So 1, and weight of this is given as 0.5. Every weight is given as 0.5. This weight is given as H2H weight is given as 0.2. So this whole weight is given as 0.2. So the output of this will be processed, the input multiplied by weight plus input. The input is 0. Initially it is 0. So 0 into 0.2 plus E, because it RNN, vanilla RNN consists of single neuron, it has one bias also, plus suppose we have bias related to the hidden unit is equal to say 0.1. okay, so this is one unit only, one neuron only, so we will add 0.1. and to calculate the output of hidden unit, we will use here we will get 0.6. This will equal to 0.6. Now we will use to get to activate this neuron, we will use the activation function, that is tan h. In RNN we use the tan h as activation function to calculate the output of hidden state. Okay. So it is equal to tan h of 0.6. We know that the formula of tan h is 0.6 minus e raised to power minus 0.6, e raised to power 0.6 plus e raised to power minus 0.6, which is equal to, we can calculate it, which is equal to 0.537. So here we have H1, the output of first unit, the output of not output, the output of H1 unit, the value of next V1 will be equal to 0.537. okay, now we will calculate Y. How to calculate the output of Y? Y will be equal to, here again output will be calculated with the help of one neuron only. So this neuron will get input from the hidden unit, that is one input is from hidden unit. Hidden unit's output is 0.537. What is the weight associated with this neuron? It is 1 multiplied by 1 plus if it has any bias, because every neuron has its own weight and bias. So bias associated with output layer, say it is 0.05. So we will just add 0.05 here, and Y1, output of Y1 is equal to 0.587. It is equal to 0.587. So this is the summation of this neuron which is located at a output layer. To calculate, to activate this neuron, we have to use one activation function. So here we are using the sigmoid function. So sigmoid of this value will be equal to 1 upon 1 plus e raised to power minus 0.587, which is equal to 0.642. okay, which is equal to 0.642. so in this we can say the when we in the first layer with input 1, we are getting output as 0.642. Here Y1 is equal to 0.642. Similarly, we can calculate it for another hidden states.